Well, welcome back. We're going to give this another try. Sorry about all the technical difficulties we had the other day. I never thought that plugging my headphones into my computer would cause such havoc. But we'll give this another chance here. And I know a lot of people who got on the seminar were there really because they wanted to just see a neural net, see a neural net being built. I think this is a nice little example. Uh, while it's very representative of a certain kind of neural net, I just want to make sure everybody understands that there are really a lot of different kinds of neural networks that you could build. Uh, the one that I'm doing right now is one that we tend to call a feed-forward regression type network. In fact, it's probably the most popular one that's out there. It's called the backpropagation paradigm, and it's been around since the probably about 1987, I think, is when it got really big. But it was actually done in papers even before that. There were actually student papers that laid out some of the foundation for this. And if you go back all the way into the 1940s, you see some papers that were written around this subject. But anyway, it's an interesting problem because it really helps us overcome one of the really, I don't want to say hardships of doing statistical regression, but one of the more arduous tasks in doing statistical regression, and that's actually trying to determine what the model is. Um, I know all of you who've had Stats 101 have done an analysis of variance and used it in statistical regression, usually linear problems, where what you're trying to do is basically fit a line to a set of data, and then have that line. That line in the end, it basically generalizes the problem. Of course, to do that, what you're going to try to do is minimize the amount of error that could happen between the line and reality, what we typically would see in reality. So you start with a sample of the population, and you fit a linear onto it, and we do that through this technique of regression, where we analyze the variation and we minimize the overall root mean squared error, or we try to do that. And we do that by having what we call a goodness of fit parameter. I mentioned the other day, for those who were able to stay on that, if you recall back, there are some rules of thumb about what constitutes a really good fitting regression model, whether it's linear or nonlinear. And we use those goodness of fit tests to say how accurate we think the line we draw from the sample fits the population. So we kind of could do the same thing with a neural net. We could do a mapping function like that, where we could map independent variables to a dependent variable. Uh, with neural nets, though, one of the incredible strengths of it is that you could also map many independent variables to many dependent variables. In other words, where your regression models tend to be x's to a y, in neural nets we could actually have x's to y's. Okay, and I mentioned, one of the things that I appreciate a lot about doing multiple Ys is because sometimes we have correlation among our different output variables. When we try to separate, have different models for each response variable, then we kind of lose that inherent correlation that could exist between the Ys. And I did say something that was a little bit out of step yesterday. I said that, one of the things that statisticians like with regression is the fact that, in fact, they want to do with regression is remove as much correlation as possible. Now, that's not 100% true. Okay, yeah, in linear regression, in the x's, you bet you like to have as little correlation as possible. But obviously, especially in nonlinear regression, we try to accommodate that by having um, uh, values that are raised to powers, or factors of each other. We could have x1, x3 as part of our equation. And any kind of function really. that nonlinear function, we could model that, but we typically have to try something. We have to go and say, well, let's try x1 times x3 in this one, and or x2 raised to the sixth power, or whatever you're doing, something that makes it a nonlinear model, basically, and yes, there are some things you could look at in your analysis of variance that could give you guidance as to which input parameters to pick on at any given time. They may even give you some indication about which ones aren't even contributing overall. But you still have to build that model and then do the analysis and see how well of a goodness of fit you could actually get for it. Typically, we look at the adjusted R squared value, and we want to get that in a range of over zero point 0.8. Okay, even though sometimes lesser is even sometimes good enough depending on the problem. Well, here we have a problem where, at least in a linear uh, regression mode, we can't get to point 0.8. We don't get to point 0.8. This is an actual real world problem that was done back in the 70s to do, to make a prediction about fuel efficiency in cars, given certain engineering characteristics of the car, and then where it was built too. That's part of this. Um, Now this is an example where we have, you can see our independent variables, the cylinders, the weight in tons, the drive ratio, the horsepower, the displacement, and then the country that the car is manufactured in. We have 38 um, we have 38 cars basically in here that we've sampled data from. And then they have actually gone out and measured in use the average miles per gallon that a car will get. They didn't say if they operate at a certain speed on this. That's kind of interesting. I wish they had done that, but we'll go with it. Yeah, we'll just all these. Maybe it was 30 miles an hour or something like that. We'll say. Okay, so then looking at this, then you can see right off the bat we got a situation where our country, the manufacturing country, is not a number. It's a category basically. All right. So right off the bat, you could do one of the things you could do is you could separate the data from each country and create a model for each one. But they wanted to try to see if there was a common model they could come up with across any country. It would work for any country. So they did the statistical regression utilizing all the countries together. All right, and the thing about this that was kind of interesting. I'm going to give you a little bit of the solution away right off the bat. Turned out the country didn't make a difference. Okay, we were able to actually toss out that independent variable, if you will, and just utilize the other ones. And even some of those in the end, didn't make that big of a difference. But anyway, having said that, you need a way to represent this semantic variable, basically. So obviously, if you think back to how you did regression, one of the ways to represent this is through binary variables. So with three possible values here, you would need at least two uh, uh, independent variables to do that. Okay, so to represent it in a binary fashion, one, two, and three, let's say. So maybe I make the US one, so I would have uh, in this case an X. I think this would be, let's see, X8 and X9, or no, X7 and X8 would be 0 1 for US, maybe 1 0 for Japan, and 1 1 for Europe. Okay, now that's how I would do it in the statistical model. In neural nets, it doesn't work out that well. Sometimes it would have a hard time distinguishing Europe from the other two because it shares a lot with the other two, basically, as far as the pattern goes. All right. So what I'm going to do in my model is I'm going to have a variable for US, a variable for Japan, and a variable for Europe. Okay, so in other words, if it's US, the variable for US will be one, otherwise it'll be zero. So I will get unique combinations. I'll have zero. I'll have say 100 for U.S. I'll have 010 for Japan, and I'll have 001 for Europe. And that allows me to hit now not to have any kind of overlap between the two. If somebody would ask, well, what about 0000? Well, that's kind of an unknown situation then, and that's kind of neat that I could actually have an unknown situation then if I want to do that. Okay. Anyway, another thing I want to point out that I didn't yesterday is look at the magnitude of the numbers. In regression, magnitude doesn't really make much of a difference. It's going to be able to handle that, okay? But in neural nets, the nature of the computation, something like displacement being so much bigger than weight, we could actually see computationally that displacement could overwhelm the network. So one of the things we're going to do is try to um, scale these things, scale and normalize these numbers in a range, and use that common range throughout all these. Now, something somebody pointed out to me once too is cylinders, even though they're numeric, they also tend to form categories. Look, you got 8-cylinder, 4-cylinder, 6-cylinder, and then we got this one oddball that's 5-cylinder in here, this Audi 5000. Okay, well, it turns out that's up to me now. How do I want to model that? I could try to do this like I did the binary one over here and say eights are just one and fours are two and sixes are three, and maybe I'll just ignore the five or something like this. But I could also model it like this, just as a number here, and that's what I'm going to opt to do on this. I'm going to just make that a number, and again scale it in the same scale that I do the other ones, which will be not necessarily 0 to 1. Okay, I'm going to do some uh, yeah, actually, on the input, it will be 0 to 1 for at least one of the models that I'm doing. Okay, I'm going to scale them between 0 and 1. So I've got 38 patterns basically here. And by the way, do I need to do anything about the name of the car? No, I don't. Okay, I will. That's information. That's information that doesn't mean anything. Okay, so we're going to not worry about that. We're going to have 38 patterns here. I need to train the network, but I don't want to train it on all the patterns. I want to train it on a subset of it. The reason is because I want to keep some behind so I could test it to see how well did it generalize. In other words, when I show it something it never saw before after it's been trained, does it still do a pretty good job of mapping? If I measure the RMS value of the test set, is it within the ballpark, basically, of what I trained it on? Now, this is one of the things that we struggle with. What does it mean to be within the ballpark? If I was to do a training and get an RMS error that I thought was satisfactory, and then I did the test, and my test RMS came out, say, 10 times what the training RMS is, I probably didn't really generalize enough about the problem. There's something in that test data that's causing it to introduce a lot more error to it. Okay, it could be that my test error may have an outlier in it too. Okay, we're gonna actually see that in this problem. All right, but anyway, what I want to do is get something that's relatively in the ballpark, knowing that typically the test error will be greater than the training error was, simply because there will be phenomena in that test data that I may not have fully captured, but yet I still have a model that's good enough because it had a strong goodness of fit. So this is my challenge. This challenge I give to my students. Take this model where we've already used regression and come up with a fit and see if you can do better than what they did. Now, I don't actually have, unfortunately, the nonlinear model that they ended up with. I know that its goodness of fit was somewhere. I want to say it's 0.84. It may only be 0.82. Both of those ring a bell to me for some reason. It was definitely over zero point 0.8, okay, which is a good model, okay, statistically speaking. Here I went out and just in Excel ran a linear regression model, created a linear regression model, ran a linear regression against the entire data set. And I came up with an adjusted R squared value of 784. Now, there's a lot of other things that are going on here that I point out in my class. I'm not going to do that right now. I'm just going to concentrate on that. Right now I got a goodness of fit of 0.7284, and I know that that is not really a great fit. I want to do better than that. Okay, so what I did is I went and created a worksheet, a workbook that has this information in it, and while I can get an R squared value from my neural net, okay. Uh, First off, I'm going to be using an old software package, and when neural nets first started out, I mean they just focused on RMS, so I'm just going to do RMS here. Root mean squared error. Okay, I want to try to find a lower root mean squared error than I got in that linear regression, basically. So what I did is I went back and I actually went out and figured out what right now, given these are my 38 patterns, given those right now, what is the regression value compared to what the desired was, and then that becomes the regression error, and then I I square those, sum them all up, and take the root, and I get the root mean squared error, and it comes out to be 2.17. Okay, that's good. Now that's my basis. Now what I want to do is I want to go back. I want to go out and create a back propagation neural net, and I'm going to start out with just an arbitrary number of processing elements in a couple layers of hidden layers, and try this on this problem. Okay. Now again, I need a training set and a test set. What I'm going to do is I'm going to use the first 32 patterns that are in here to train the neural net. In other words, I am going to try to find a minimum point in space where the RMS error is better than what I have in the regression model, just based on these 32 patterns. I'm going to send those through the network, calculate an error, an overall RMS, and then take that error and propagate it back into the network, adjust the weights based on how much they contributed to the error happening. And then I'm going to do the whole thing again. I'm going to do that over and over and over, adjusting the weights in the network until finally I get to a weight matrix, basically, that has that we call it converging, a convergence for the error, that where the error value is very low. And at that point, I should be able to see an RMS error that is hopefully better than what I had in this statistical model. But I'm also going to reserve these other 6 patterns here to test it. Now, when I test it, I'm going to test it using the ones I also used to train it, but then I'm also going to have these extra 6. So what I should see, like I see here, is the RMS, what we call recall or recall test, regress, will be higher, and usually just a bit higher, not magnitudes higher or anything. Okay, but here you see it's a bit higher, meaning that if I when I look at just the training patterns, if I just took them, it's 2.17. I add the other ones in, it comes out to be 2.87. There is some other phenomena that's not being generalized just based on the first 32, in other words, and that's typical. We will usually it is incredibly rare to see this be the same number. You never see it be less. Okay, there is always something there that you haven't captured, and it's always going to influence the more error in the model. So anyway, let's go back and try to create a neural net to do this now. And when I build this neural net, I'm going to not only use the independent variables that I have right now, these ones right here, which were my horsepower and my drive and all that, and the cylinders and all that. But I'm also going to have an independent variable called the bias. This is something we do in neural nets. In order to keep things moving, it really helps to have bias on each of our nodes. So we're going to have a bias B where basically it's just an input value of 1 that's constantly being sent into the network. Okay, I'm not going to go into a whole lot here and show you bias and how it works and all that. I'm just going to ask you to trust me that there has been an absorbent amount of literature written about bias and how to and why it's important in neural nets. Okay, and yeah, there are some neural networks where you don't need to have bias, but in the backpropagation model, keeping your bias on through the whole thing does tend to help speed up convergence. So the first network I'm going to build will have these 8 inputs. Okay, the I should say the 8 inputs plus the bias. Is that right? Let's see. Yeah, because bias happens automatically. I don't have to do anything on that. It's going to be there automatically. So the 8 inputs that I'm going to have are x2 through x9, and x7 through x9 being those binary variables that represent the country. So I'm going to have an input of 8. I'm going to put 5 in the hidden layer. I'm going to have 3 in the second hidden layer. These are processing elements, and then 1 in the output layer. The elements of the input layer do nothing more than just distribute the input values, these x values, into the network. There is no transformation of the values, but at each of the processing elements, we're going to transform the collective signals that come in from all arcs. And it's just a weighted sum, basically, and the weights are the weights in the network. Okay, we're going to do a weighted sum, and then whatever value that is, we're going to subject it to a sigmoid function. A sigmoid function that ranges between 0 and 1. And again, remember, these input values are going to be scaled between 0 and 1, scale and normalized between 0 and 1. So we will subject it to a sigmoid function at every processing element in each of the hidden layers and the one that's in the output layer. We have one output from this, right? We have a 1y value. It's our miles per gallon. Again, we could have many, but we have one in this case, all right? And it will also do a transformation to the output of this. So sigmoid functions are there. And we're going to use our training method will be to actually present every one of the training patterns to the neural net and then figure out the overall error based on those 32, and then we will back propagate that to the weights. Now I could do it for every single pattern if I want to. I could back prop the weights, but it has actually been shown mathematically that it is more efficient. It's obviously a lot quicker, but it's actually more efficient and you get convergence a lot quicker, a lot smoother, I should say, if you do the overall error rather than individual pattern errors. Then you also get into a situation where if you do what's called epic training, that we do all 32 training patterns at once, then you won't have a situation that you can have two patterns contradicting each other and it causes it to learn and then unlearn. Okay, because it's doing it all together. Okay, in other words, I don't have to worry about the order that I actually present the patterns to it. Okay, I could do keep the order the same every epoch if I want to. All right. Whereas if I do patterns, then I could have a situation where I have a pattern that would make the error better, and then the next pattern makes it worse, and those two are basically off. You get a cycle basically of better, worse, better, worse, better, worse, better, worse, to the point where I actually have to random show those to the network. And there I could do that. There are learning rules where if I elect I want to do it that way, I could do it that way. Okay, but again, it's been showed statistically that this thing that we call normal cumulative delta rule, the taking what I call epic training, is really the best way to do it. And so that's the way I'm going to do it here. Now you might notice too, there are some other parameters in here. There's what's called the learning coefficient that could be associated with every PE in each of the hidden layers. That is basically in the sigmoid function, there's a rate in that equation. And I could set that rate so that the calculation comes out higher or comes out as a partial of that, basically, okay? And that could either slow or speed up training, all right? Well, you might say, why do you want to slow training? Excuse me. You got to remember, we are Our error function is going to look like a landscape, a hilly landscape, and we could get caught in a local minimum. And sometimes the learning rate might take me to a local minimum right away, and even if I have momentum or anything else that's on there to try to speed, I may just get stuck there. Okay. The other thing is I could traverse that range incredibly slow. That it takes. I mean, you're going to see we're going to do millions of cycles on these, and yet they're not going to take us that long. That's simply because my computer is really fast. Okay, compared to me doing it by hand, obviously. But believe it or not, there are neural nets that sometimes will take days, weeks, months in order to finally converge, depending on how complicated they are. What we're going to do is not going to take that long, just a minute, I think, at the most for one of these. But anyway, with having said that, okay, learning coefficients help change the nature of the transformation. Okay, but then we also have a thing called momentum, which is actually an additive to the sigmoid function. That in the case where, let's say, you've gotten to a local minimum, momentum may be enough to kick you out of it so that you can find an even better minimum somewhere. Okay, now again, this problem is not that complicated. The odds are we are not going to have a problem. If we do get into a minimum, it'll get out of it fairly readily on its own. In fact, I know that simply because I've done this a million times. All right. But there are some where the difficulty, it may be incredibly convoluted, the data that you have, and then you probably would want to have a momentum term. Again, there are rules of thumb of how to set that. If I did it here, it would be a constant thing that would be on throughout the whole training, but I can actually have it so that at certain points it actually degrades it a little bit. So, and then there's things like adding an offset. If you think about the sigmoid function, the midpoint is typically the mean of around the mean of the population. Okay, it could be okay, but what we could have is we could actually have things that are really tight around the mean that cause it to flip back and forth. In other words, I'm in the negative part of the range, and now I'm in the positive part of the range, and I keep going back and forth to the point where it actually starts paralyzing it. That's actually a word, and we call it the paralysis of the network. It gets to a point where it still should be learning, but it can't because it's trapped between the situation where it's moving from negative to positive. When the network senses that, it can actually just do a quick offset of the of the activation function, just a little bit, to see now, did I force it into either a negative range or a positive range? Okay, it's not something that you usually have to worry about. Okay, but when it happens, boy, it's frustrating. You see a network that just sits there doing nothing. Okay, and it's not because it got stuck in the asymptotic regions of these functions. Tan H, sigmoid, sine, they all look like S's, right? They all have a lower and higher asymptotic region. What we want to have is training happening in the region where you got the most gain, which is the middle of the S, okay? Where you go from not knowing anything to knowing something as quick as you can. That's what we like to see. But we could even manipulate the slope of that function and slow down training. It might make sense to have one set of PEs train slower than another. We see that phenomena happening sometimes. And so the learning coefficients give me the opportunity to do that. I am going to have this parameter that's called min max, which this is where it will actually scale and normalize my data for me, and I'll be able to say what the range is I want on that. The learning rule, again, I'm going to use norm cum delta, that is epic training, and I'm going to use the sigmoid. Sometimes you'll hear it called the logistics activation function, but it's just your from trigonometry. It's just our sigmoid function. Sine functions, tan H functions, they look the same, but they have different characteristics. Sigmoid ranges between 0 and 1. Tan H ranges from -1 to 1. Sometimes bipolar is better than binary. We'll start with binary and see how that goes. And I've got these two files here that it basically set up my training patterns and my test patterns. Let me show you those right now. I can remember where I put them. Okay, there they are. Okay, I have a file called P01. This is project one for my students. Underscore L. That means learning. This is the learning set. And if I open up, you'll see it's just a text, ASCII text file. And here's my X values. So my cylinders are first, if you remember. And then I get these zeros, 1, 0. This is my country. There's my binary variable. And then finally, the last column is my Y value that I'm doing. Again, I only have one response variable here. I could have had many Ys. We're basically making regression. We're doing a mapping here of our X's to our Y. So this was data that was measured. This was an output that was measured. We're going to put all these 32 measured patterns. We're going to feed that into the network as an epic, compared what we actually got, compared to what comes out of the network in that last processing element in the output layer, to what we desired. We consider this to be our desired value, and the difference then is the error for that pattern. And again, we're going to square those errors, add them up, take the root, and then that will give me basically my root mean squared error for that epic. And I'll repeat that over and over and over until finally that root mean squared error hits a point where I feel, yeah, that's good. I've minimized the amount of error that I have in my network, and I've generalized this thing as good as I'm going to. Now here's the recall. Oh, I'm sorry. That was the actual recall. Here's the recall set. Okay, it has the same 32 in it, but it also has 6 additional ones that we're going to use to test it. When we test, we only send this thing through once, and we figure out what the RMS here is for that one pass that we do, and we'll see if that is in the ballpark. So the software I'm going to use to do this is called NeuralWorks Professional 2. This is a 1990s software. Okay, you can tell right now it is not graphics based. It's actually text based. It runs in Windows. Okay, at least they got it that far that I could run it in a window. But it's an old DOS based system, and you know what? Even using this on 286 speed machines back then, it did a really good job, at least on what I would call textbook problems. It's an excellent environment. It's easy to learn, easy to use, and it really surprises me that I haven't come across anything else among the new software packages that I think are as easy to use. R, Python, MATLAB, they all have neural net packages that you can buy from. They have script-like commands, functions, if you will, for setting up the different kinds of networks and all that, which gives you a lot more flexibility if you want to actually program this stuff and all. But the actual putting it together, having a user interface to actually graphically design this thing, I think they're sorely lacking. I don't know why they haven't done something like that. This is interesting. It's going to help us build the network. It'll help us train the network. Once we converge on that, it'll let us test the network. And then it'll give me, if I want a printout of what that topology looks like, what the weights are, all that I could go back then and I could actually create a C program. In the case of what I'm doing here, a spreadsheet that actually captures the network, basically, that I could then deploy if I want to. The other thing that's interesting about this software package is once you do have gone through and trained it and you're happy with it, all you have to do is push a button and it actually generates the C code for the neural net. So then all you have to do is bind it up and put it into whatever software program I want it to work in, as long as it gives me the capability to do that, link it to it, whatever way it is, and then I have the ability to utilize that as if it's a gray box in my software. So anyway, said a lot about it. Now let's build it. Okay, I'm going to go into this thing called InstaNet, and you'll see there are already in the scene some canned neural nets, some of the more popular ones that you would do. There's the generalized regression network, which is even more general than the backpropagation network. But I'm going to use backprop. Backprop again is historically one of the more interesting ones. Academically, we use it all the time because it is a good introduction to neural nets using backprop. It is something that we could relate to because most engineers have had a regression modeling class and can relate the two of them. But again, there are other types depending on the type of problem you're doing. I'll talk about that a little bit at the end here. Okay, so let's build this network. I said I had 8 inputs into it, eight x values beside the binary value, which I get automatically. I want 5 in the hidden layer. Where did I get that from? I am just picking a number. This is how you do it. You start. Now what I do is I kind of like, well, I've got 8 inputs. I've got 1 output. It can't be that big of a network, okay? It's got there's problems if you make your network, if you oversize your network, you keen size your network, it may run the risk of not really generalizing the problem. And in fact, that's what's going to happen here. I'm going to give you a little heads up that where we're going with this particular one, it's not going to generalize it, even though it looks like it did a good job of learning. All right, I'll get to that in a minute. I'm going to put a second hidden layer in here. All right, now I will tell you, usually smaller problems, you don't need more than one hidden layer. If you go to 3 hidden layers, you're probably doing something wrong for most problems. Okay, now there are what they call deep learning neural nets, but they're a different kind of neural net. They could have, I mean, I am not exaggerating, literally tens of thousands of hidden layers. But for a typical mapping function, typical regression type model, usually one hidden layer is enough. And there's actually been papers written that show that anything you could do in multiple hidden layers, you can really do it. If you could get a network to converge and generalize, we use in multiple hidden layers. There is an equivalent single hidden layer neural backpropagation network that will do the same thing. Okay, it doesn't mean they're going to have the same number of PEs. You may, let's say for instance, let's say this one does generalize and I do it with 8 PEs and 2 hidden layers. It could take 100 PEs in a hidden layer to do the same thing that those 8 would do. All right. Conversely, it could just take 2 to do, and maybe even do better. And we're going to see that in this case. Okay. But anyway, I'm going to start with 5, and I'm going to set the coefficients a little bit high, just because I don't want this to take all day, and actually it won't take all day anyway. I usually set the first one high and the second one low. It's kind of like I use the analogy of tuning on the old style TVs where you had the big tuning dial that got you in the ballpark, and then you had the fine tuning one, the little one that kind of zapped it in. That's what I'm going to do here. I'm going to run real fast on the first layer, and take my time learning in the second layer. That's pretty? I mean, that's not truly what's happening here, but that's a pretty good way of explaining it for now. I'm not going to put a momentum turn on here. I know I don't really need one on this one. So, and the I can even set that the overall learning coefficient, which basically is the stretching of the of each processing element. I could set that, and I'm going to do that. And I'll leave the offset at 0.1. It's fine. I don't need a lot of this jazz here. I could force this into bipolar inputs versus binary inputs, but I'm going to stick with binary for now. It's fine. And then I'll have a min-max table. And I have to set up my input file. So here's my learning file, the P01_L. And then I also have to set up what my test, or what we call the recall file is. And again, it's going to be P0. I went the wrong way, sorry. P0_R. Okay, so there's my learn and my test. Again, the transfer function I want to use, and I often get asked, can I mix my transfer functions? You could do whatever you want, but you can't do it through this setup tool right now that I'm using right now, this canned one. I could actually go in here in raw NeuralWorks and go in and design each processing element if I want to. But you know what? I can't think of a time I ever really needed to do that. So I typically will just pick one and say I'll use sigmoid throughout the whole network. That's fine. And then I went norm cum delta being epic training. Although here you see the epic right now is set to 16 patterns. Now that's an interesting thing. I could have an input file that has a lot of patterns in it and say, do epic training, don't use them all right, in an epic. So let's say I've got 32 in here now. If I did 16, what it would do is it would train the first time through using the first 16. The second time through, it would use the second 16. The third time through, it would go back and use the first 16 again, and we just keep repeating that over and over and over. Again, I don't know why you'd want to do that. I just always set the epic from the file. So I'm going to train with all 32 that are in the training file right now, the learning file. Okay, again, in the test file, we've got 38, and that's what we'll use to test it. So I say okay now, and it's actually going to create a little graph of what this network looks like. Now, I know typically when I show it in PowerPoint, you see the neural net with the input on the left and the output on the right, and it's horizontally depicted. Here it's vertically depicted with the inputs coming in at the bottom. So you'll see bias 1 is my x1 value, and again, that is always a 1 going into network. The weight associated on that arc will be trained just like the other weights are, okay? But the value going in there will always be 1. 2 is my cylinders, and then I got my horsepower, my displacement, all the other things I was measuring. And finally, 7, 8, 9, those are my binary inputs that are going to describe what country the car was made in. Here you see the first hidden layer. I have 5 processing elements, again, all with sigmoid functions, and in the second hidden layer, 3 with sigmoid transfer functions on it. Again, what's going to happen here is the signals will come in, they'll be multiplied by the weights on their arcs, and then at the processing element in the next layer, they will be accumulated, and that will be the overall signal going into that processing element. Then they will be subjected to that transfer function, that sigmoid function, and basically modified. That will then be sent then to the next, and the same process happens there until finally it gets to the last one, does its weighted sum, and gives me an output from the network. That becomes my my actual output from the network. And I compare that then to the target, which is the Y value I have in that pattern, and whatever the difference is, that becomes the error for that pattern. I do that for all the patterns. I accumulate the error for all the patterns in that training epic. And then when that's done, I send it back into the network, adjusting the weights of these arcs, even the bias arc, based on how much they contributed to the error in the next layer. Okay, I said to the overall before, but really what I do is I say, I've got an overall here. What did these all contribute? What was the error they all contributed? And then I update them based on how much they contributed. And then I say, okay, well, what was the error on each one of these? And I say, how much did the arcs that contributed to that error contribute to that error? And I update those, and I keep going back until I finally get to the input where the processing element doesn't do anything except distribute it into the network. And then I go through the training again. I do it again, and I do it over and over and over, and I keep adjusting those weights until finally they pretty much stabilize. There may always be a little bit of flex in there. You might have some that flip back and forth a little bit, But the fact of the matter is, overall, it does stabilize. It generalizes on something, hopefully. Okay? Now, I'm going to do this training. I got to somehow understand that what's happening at any given point. I got to actually see something to know how well it's doing, right? And it turns out there are a lot of things you can monitor as training's happening. You could create a confusion matrix of and actually see which elements tend to be firing the most or the strongest and all that. You could have you could look at the network weights themselves and see how they're progressing. You could do them individually or collectively. Correlation and RMS error tend to be the two that people use the most. The correlation between the input and output, and say how much it's actually being strengthened there as you go along. But the RMS error is the one that I always use. I always put at least the RMS error control on the screen, because that is where I'll see the nature of the RMS error. I should see it coming down as the training happens. So I'm going to say, okay, I'm just going to use the RMS error on this one. And again, it's not graphic based, so I have to do some interesting things from back in the 90s in order to make it look a little bit more graphical. But anyway, here it is, and you can see the RMS error. It's being scaled between 0 and zero point 0.5. Zero point 0.1 tends to be a level that is acceptable for a low RMS error. Okay, now on a problem like this, where it's pretty clean, it's not a huge problem, I would probably want even better than that. I would like to, in fact, probably getting down to 0.01 would be a great thing. I'm going to say anywhere in the ballpark on this one, of maybe about 0.05 or so, would be good enough for what we're doing right now. So I'm going to monitor the RMS error here. And one of the things I want to make sure first are about the nature of my input and output parameter. And you can see that here. My input starts with the very first column in there, and it goes all the way to the ninth column. So I've got 8 columns. Remember, I don't have my bias showed there. So I've got my x2 through my x8 values, and I am going to normalize them, and I want to normalize them all the same way. They're going to be normalized between 0 and 1. And you can see the network knows that this is a backprop, and then I'm using a sigmoid function, and that really I should try to scale it to the same scale that I typically would have for the high and low end of a sigmoid function. Same thing with the output, except there's an interesting phenomenon that when you're in the asymptotic region, things tend to slow down. So one way to get over that, believe it or not, is to scale your output so it's something less than 0 and 1. And so what we're going to do is we're going to scale it between 0.2 and zero point 0.8. I have studied this over and over to see, does this really make a difference? It does, but I can't explain exactly why, other than like I've been told. It's got something to do with the fact that you're working in the asymptotic regions when you're at 0 and 1. Why it isn't a problem on the input, I don't know, but on the output it tends to be a problem for some reason. Okay, I'm going to turn on these things. These are the things that actually generate a file that tells me the architecture, spells out what the architecture of the final network is after I test it and all that. And then it's going to reflect to again that my learning and my test files, they're fine. I don't have to do anything to that. All this other stuff is good to go. One of the things I do, I could actually say here if I want to show things sequentially or randomly. For backprop, it's just going to do it sequentially because I said I wanted to use Epic training. But I could turn off these things. One of the interesting things back in the 90s, again, our computers were a lot slower back then, and we found that loading the network entirely into memory and running it was a lot faster. Okay, in other words, you didn't have to keep going out to the file to grab the problem. We actually loaded all that data into memory. It meant you had to have enough memory on your computer to be able to hold all the data at one time. A problem like this, it would be able to, no problem. Now, with computers being as quick as they are and with dynamic memory allocation, you really don't need to load things into RAM anymore. You can just let it go and let it work from files. So I'm going to just do that. It tends to be a little less error prone. I've had things in memory where it just kind of barfed out after a while because it overloaded the memory buffers. I don't think that would happen with today's PCs, but in the old days it happened a lot. So I'm going to say okay. I know I'm giving you a little bit more than I intended to here, but since I'm recording it and we got a little time, why not? Okay, so I'm all set up now. I want to look at my instrument though. Actually, I'm good here. I was going to say I could change the axis if I want to. I could change how often it puts a point in there. I'm just going to let it plot something. I think it does it every I want to say it's every 10 epochs here it'll plot. So every 10 times it actually has shown the training vectors, it'll plot out what the RMS error is. I think that's the case. I don't think it's doing every time. Yeah, I think it's every 10. But anyway, let's go and run this thing now. So now I'm going to learn. I'm going to take that input, that learning file, all the patterns in there, and I'm going to present all the patterns 500,000 times. Now, I'm going to tell you right now, if you had to do this by hand, in fact, usually in my class, I make the students do one pass of a network by hand, just so it impresses upon them how much the computer is helping them here. All right? I guarantee you, a single pass doing all the calculation, if you had to take a calculator and do this by hand, it would take you probably at least, and this is if you're really good at it, at least a half an hour to do one pass. I would not be surprised if it could take you 2 or 3 hours if it's new to you doing this. Okay, it is a lot of computation, but here's the cool part: it's a lot of easy computation. One of the things I didn't talk about, and I won't talk about in any detail here, is the nature. There's a reason why we're using that sigmoid function or the tanh function or the sine function. They're invertible and they're continuous, which means I can backprop by taking the inverse situation. And it turns out the equations to do it on those three, and there's other ones, are incredibly easy computationally. Deriving them, oh man, what a chore. I mean, one of the great derivations I ever did in my life was to deriving the generalized, what they call the generalized delta rule of learning. When I did that, I realized, hey, I finally know math, because it is incredibly terse. Trying to come up with how you take input and how you calculate the back propagation from it. And you looking at the equations, you would go, oh my gosh, how could this ever be simple? And at the end, it becomes something incredibly simple and elegant. And that's why neural nets lend themselves to solving incredibly difficult problems. They basically simplify things through the use of parallel computation. And I know that probably doesn't mean a whole lot to you right now, but if you ever get into this subject, that will dawn on you at some point, and you'll realize that's why this is different than everything else we do. So anyway, I'm going to go ahead right now. I'm going to do these 500,000 cycles. Again, using those real simple formulas that are embedded in this thing, but with a very elegant and theory behind it. And here we go. Now watch the RMS error graph after I hit OK, because this is going to happen very fast. Did you see how it came down really fast? And this is a phenomenon we see in neural nets all the time. At the beginning of learning, they learn a lot really quick, but then it takes a lot to refine it. You can see the RMS error is still coming down here, but a lot slower. Okay. All right. Again, I would like to get this down to 0.05. All right. But it's going to keep going. Okay. Now, it stopped at 500,000. I didn't get that far, right? I could keep it going. I go back and, well, okay, run another 500,000. But look how it didn't take very long to do 500,000 cycles of that. If I had to do billions, is that a big deal? We've done some in class where I did one night where I went to bed, got up in the morning, and it was in the hundreds of billions of cycles. And believe it or not, the thing was still converging too. And that's the thing. People ask me sometimes, how long do these things take to learn? This is the hardest part of getting people to accept neural nets. They may not. You're going to have to sometimes play with the data and get more data and do all kinds of things in order to get them to generalize. And even then, there's no guarantee it's going to happen anytime soon. It's been my experience that most problems, they converge really quick, or they take forever to converge. Okay, when I was doing my dissertation, I actually worked on a neural net that took a week. A week. Now again, 286 machines. In today's day and age, it probably been less than a day. But back then, it took a week for it to finally get to a point where it converged. And you know what? It was a good generalization after a week. The other thing is sometimes you see phenomena where it trains quick, sits there, and then trains quick again and sits there. It's just a matter sometimes of the weights getting into an area where now they are really in a whole different part of the error state, and now they have the ability to learn quick. They find a new. The generalized delta rule is just a gradient descent method. Okay, sometimes those gradients level out and not much happens, but then suddenly they get steep again, and man, you go down that gradient really fast. And that's what you see at the start here. Usually the ball, if you're falling into the landscape is what it amounts to. And then you play around in the landscape, you know. And if you are really getting in a minimum that is either the global or very much like the global, it could really slow down until it finally gets to the bottom of that bowl, you know, because you're in a very, very low-lying range. You know, it doesn't have a steep gradient to it. So I'm going to stop this one here. All right, and I'm not going to test it, okay, because I already know something about this one that you don't, and I'm going to explain that to you. I took this 62 million cycles and I got it down to 0.001. That is incredible to get an RMS that low. In fact, it was so low that I was suspicious. So I went in and I looked at the actual error that I received in doing this on every single pattern. And look what happened. Some of these have no error whatsoever. It's really low. And then you got this one that's really high. And then when I did the testing, guess what? I even had a couple of them that were really low, but most of them were significantly higher than the other ones. Okay. I basically over engineered this network. I put too many processing elements in it. What ended up happening is it didn't generalize, it memorized. It memorized each of these patterns. It did not generalize across them. So I got a problem. This network will never work. I could never deploy this as a forecasting tool. Unless something was exactly in one of these, I would probably be way off. Like like this one, these down here. All right. So what I want to do is I want to do this again, and I want to basically decrease the number of processing elements in my network. Yeah, you know, it's interesting. There are variations of backprop where if that happened, it would stop it and actually take out some PEs for me automatically. In fact, I could go over to that model I have right now and just remove some and continue on and see what happens. Okay, but you know what? I've found it's a lot easier just to start over and do it from scratch. You know, that way I don't carry over any bad baggage that I may have learned already. Okay, so I did this one again, and I used the sigmoid function, and this time I only used 3 in the first hidden layer, and I got much better results. Look at compared to point. Now this one did good. I mean, compared to the regression, but again, we know there were problems up here. What I really want to see is something like this, where there is some error. You know that I've generalized, but the error is acceptable. All right. And look at for most part, these tend to not be too big, you know, in relationship. You know, between 0 and probably 4 is not a bad error, okay? And most of these things are under 1. So I've done a pretty good, I think I've done a fairly good job of generalizing. I have definitely got my root mean squared error below what I have for the linear regression model, so it's doing better than the linear regression model. But you can also see there's some other things that are already signals here. And I won't talk about now because I'll talk about the next one. I was curious. Now you can see too, that only took me about 2 million cycles to get there too, to get down to 0.05, which is really good. I could have stopped there and I think my boss would have been happy with that. All right. But I wanted to see if I could do even better. So one of the things, again, I'm a big believer that bipolar information has a lot more information in it than binary information. So I decided to redo this whole thing using the TANH activation function on my PEs. I'm going to run that again, the whole thing for you again, doing that. I'm going to go through this a lot quicker this time. So I'm going to go to Instinet, do backprop, and you see everything I had before is still there. This time I'm going to change the hidden in the first to be 3, none in the second. And I'm even going to slow down the learning coefficient a little bit here. Okay, make it 0.6. The rest of this I'll keep the same. And I'm going to make this a tan H function. And we'll say, okay, you know what? I'll tell you what. Something I want to do before that, I'm going to close the whole software down because I've noticed sometimes things don't reset like they should in NeuralWorks. So I've learned a long time ago, just shut it down and start it up again. I'll do it again. Backprop, 8, 3, 1, make it 0.6. I could have left it 0.3. It probably would work. No momentum term. We'll leave all this stuff the way it is. Still norm cum delta. Turn off all the things that it shouldn't be on. By the way, I'm turning off bipolar here, but it knows it's bipolar simply because I just said make it a tan H function. So it'll do it for me automatically. And again, I got to pick my my training and test sets. There and there. And set up a training. And I think we're ready. Yep, ready to go. Okay. Now here's my network. You see it has a little bit of different configuration. Only has one hidden layer in here, but still the same inputs. And I'm going to take the RMS, and you can see now it scales between 0 and 1. Did I do that right? I want to make sure. I just want to do one quick look. Was there something I did? I got to look at my input-output parameters, make sure they're really scaling correctly. Yeah, 0, 1, and -8, -8. So -8 to 0.8 because now I've got a tan H function. Yeah, input, it doesn't matter, it turns out. It's going to keep it binary. I guess it likes binary. I could make it -1, I guess, if I wanted to. But I don't need to do that. And again, these things, I'm not going to worry about them. Anyway, go on. All right. So now let's train this thing. And I'll do the same thing. I'll train for 500,000 cycles on this one. See how quick that came down? And it had a really neat phenomenon in it. And now it's continuing to come down. It's coming down, coming down, coming down, coming down, coming down, coming down. But now, look at it. Got the 0.1611, and now it's kind of staying there. It's kind of interesting. Why is that happening? Because how many did I do actually on this one before it actually converged? I forget. 3,800,000. Well, I don't want to take that much time, but I'm going to go in here and learn another million and see if that impacts. This could be, I can't remember. This could be one of those where, again, it stagnates and then it picks up again. Huh. I wonder why that is just sitting there at 0.16. We should have been seeing some progress, but no, they're just jumped to 0.110. How many million did I say that was? 3.8. I don't think it's coming down that fast. It's going to get to 0.05 in just another. I'm going to stop the start again. Maybe I did something wrong here. And this is one of the cool things about this. It is kind of forgiving. Oh, I didn't want to do that. Instinet backprop. Okay. I better check my parameters really quick. Make sure I'm doing this exactly the way I did it before. 0.6, 8 points. Maybe my learning. I bet I didn't have that set correctly. That's why I had a high learning coefficient there. Norm cum delta and H. Everything else looks pretty good. Okay, let me try this again. And I bet I'm going to have to reboot this to do this. Not reboot it. I'm sorry. Do it again. Sorry about that. I'll try to edit that out of here if I can. Think Huffman. Come on, let's see my. Sorry, I gotta zip things down. I'm not seeing everything. Okay, here we go. All right, Instinet backprop. I had 8 input, 3 output, 0.6 for learning coefficient on the hidden layer. Was it 0.15 on the, yeah, I'm pretty sure it was. 0.15. Okay, you know what I bet I did? I bet it didn't recognize my momentum term because I forgot to put the. It's very sensitive. These are, again, 1990 technology. Learning coefficient was zero point 0.9. Yeah, I forgot to put the decimal point on the momentum. For some reason, that caused it to be weird. Um, these are off. Bear with me a second. Okay, norm cum delta tan H set epic 32. That looks like it is right. I just want them again just to make sure. 831.60, zero point 0.9. Everything's set correctly and go. Okay, so I think that's it. Here we go. RMS error. Boy, it's bothering me that's showing between 0 and 1. I keep thinking that should be another number here. Anyway, IO parameter. I'm going to make sure I really do everything exactly the way I did it last time. 0, I want to make sure that that is set correctly. Let's see. 0, 1, minus 0.88. Everything else looks good there. Okay. And now let's train it. In fact, I'm going to train it at 1,000,000 just to start out. 1, 2, 3, 1, 2, 3. All right, and here we go. Coming down, coming down, coming down, coming down, coming down. Yeah, see, now it's getting better. You know, it's interesting because it does randomize the weights, and sometimes it just randomizes. Oh, look at how much it's coming down now. All right. Isn't that something? Did you see the phenomena of how it was learning, but then every now and then, and it's still every now and then, it kind of gets worse, an epoch or two, and then goes back, You see that a lot. I mean, things are very dynamic right now. It's like a marble going on a surface that's highly, you know, convoluted. Or I keep saying the word convoluted. I shouldn't do that. Very, very rugged terrain, if you will. And at some point, it's going to start settling down and narrowing in on where it's going to come to rest. So we're training for 1,000,000 here. It's getting pretty close right now to being 1,000,000, and that to what? Not even a minute, probably, maybe a minute. To get down to 0.05. Okay. Now I want to let it go for another. Now from this point on, things move really slow, and it took another 2.8 million cycles for it to get below 0.05, which is I wanted to get down as low as the one I had previously. Okay, and after I did that, and I went in and I looked at the patterns. Guess what? I got even a better RMS. Okay, yeah, figuratively, I mean the test RMS is over double what the learning RMS is. Does that mean that there's some phenomena happening in those values that I didn't capture? The answer is yeah, but it's something I really didn't want to capture. Look at this. I've got one here, and in fact, it was the same thing over here. That one pattern has a huge error compared to the rest. What does that tell you? I have an outlier. Something that is just not like everything else in this model, and probably unique enough. In fact, I don't see anything like it anywhere else that I really don't want that in here. Now, it's funny because it turns out later on, I started doing some selective updating of this, and I actually found out that in some conditions there is actually, and I think this is the one right here, there is a training pattern that also looks like it might be an outlier. And guess what? It's the one that was 5 cylinders. How about that? It recognized there was something incredibly unique about that. Not always, see over here, but there it may have just memorized it. There may have still been enough moxie in there that one of the processing elements is basically dedicated to it. that when that pops up, it's going to map it perfectly. But the rest of it is generalized. Yeah, neural nets can do things like that too. You got to be careful about this, okay? Now, the challenge I give to my students is do experiments, manipulate the parameters, manipulate the training rule. I mean, not the training rule, but yeah, they could if they want to. But the activation function. But whatever you do, use it like you're doing a statistical analysis and determine first off, do you have outliers? Do you need all these X values? There are things that it will indicate to you that you don't need certain things in here. And as it turns out, you could do things like monitor the P statistic for each one of these to say whether it typically contributes to the overall or not. Okay. I'm going to tell you right now, it doesn't need all these. And there were two outliers in the patterns that both one in the input and one in the output. And when I eliminated those, I got an incredibly strong mapping using a very, very small network. That's the other challenge they have. Not only find the thing that they think fits the best, and when I say fits the best, it both minimizes it gives them a low RMS and it generalizes the problem. But tell me the leanest network that you had that you think would work well. In other words, the one that had the least number of processing elements and interconnections on it. Believe it or not, this thing can be solved with an incredibly lean network. And I'm not going to tell you how lean it can be solved with because that's the answer to, to this project, basically, okay? I will tell you this, though. I've never had a student come up with it, what the actual leanest network is. And when they finally see it, they just are amazed that this thing, even though it's not a complicated problem, the federal government spent millions on this. And they didn't come up with a very good regression model in the end. And that's, I can guarantee you the RMS errors that we're getting would be equivalent to being up in the 0.92 to 96 range. That's how good we've done here. And we did it in just a matter of minutes on a little PC, John in his basement, using a 30-year-old software product. These are the things that, believe it or not, there is a wealth of opportunity out there in the world. I was talking to one of our head engineers, quality engineers in the shop. He knows, and he'll be the first to tell you, he knows enough about neural nets to be dangerous. But he goes, John, after he listened to what you said, I could tell you, I don't think there's a machine in our shop that we can't do something like this on. And this is just one thing. As I mentioned before, there are neural nets for any kind of problem that you could even think of. All right, some are very general, like the backpropagation model. Backpropagation, yeah, tends to be a regression-like neural net that you use to do mapping between x's and y's. Guess what? You can map between x and x. What I mean there is, I could have it learn what the pure pattern is, and then later on, when I present x values where I may have some x values missing, it can complete it for me. Think about that from a visioning standpoint. How many things we look at where we don't get the complete view of the thing, but we as human beings still know what it is. Right now I'm looking across the room and I can see part of my big screen TV. I know that that's my big screen TV just because I know what a big screen TV looks like. I could complete that picture in my mind. We could do that with the backprop model. We could have it actually complete the picture for us if it understands the nature of that picture to begin with, okay? And I could train it to do that. I could do clustering. Okay, backprop's one of the more general ones where you could solve almost any kind of problem with it. That doesn't mean it's the best way to do it, or that it's going to do it readily, okay? There are neural nets that are actually built to solve certain kinds of problems. For instance, the idea of me completing a picture, that's really what we call an associative memory. In other words, I am associating some of what I know to all that I know. It could be that maybe I want to look at that, I look at that partial view of a back screen TV, but what I want to know is the brand of it, okay? Maybe there's something about Sony TVs that when I see just part of that image, I know it's a Sony. We do stuff like that all the time, draw an analogy. That's the thing I told you about with my daughter and Barney, right? She didn't know it was, she didn't say Barney, she said son, the Barney son, when she saw this image of Barney. We do stuff like that all the time. And there are neural nets that could do things like that. There are neural nets that could form categories for me. Maybe I don't know what the categories are, but I got a whole bunch of things and I want to say, you know what, group them together the best you can, okay? We as human beings usually have to come up with some semantic method, in other words, categories for things to fall into. But what if something is has so many different dimensions to it that it's impossible for my little brain to even organize those, all the possible significant dimensions that could be in there, especially if some of them are numeric based. Okay? Neural nets can form arbitrary categories for us. We may not ever be able to put a meaning on them, but we'll know it's a category. Okay? And given when those categories happen, certain things tend to happen that I need to be looking out for. You do stuff like that with SPC all the time, right? The other thing, obviously is what is the prototypical category? I've got all these things. What is the thing that could represent that category? We don't want to hold all the data we have. If we do, our databases will get overwhelmed. But if we could have a what basically would be like a center of gravity of a multidimensional cluster and say that's the prototypical pattern for this cluster. And now all I need to know is which ones do my things fit into. Suddenly I don't have to keep 100 X values. I may only have to keep one data point to represent the whole thing. In backprop, we can compress data. I've got 9 independent variables here. What if I want to map that to another, I want to bring that down. Okay, I don't want to store 9 independent variables. Think of what we just did. We had eight inputs, and then in the hidden layer, I had three processing elements. We basically compressed those 8 down into 3, so that all I have to do is really remember the function that transformed it down into that next layer, and then the value that came out of that layer. That's less data. I just decreased the size of my database by at least 50%. That's amazing, okay? Yeah, it means I have to remember the equation, but that equation, I use that on every single pattern. I don't have to store it over and over and over. I store it once somewhere. I store it as a rule in my database and then the actual 3 outputs that I got. The rule that caused those outputs to happen, and then the 3 values. That's all I need to store. That is absolutely just 50% of the data that I had to begin with. I just compressed my data. I could tell you, if I walked into a manager's office and I said I can knock your data down in half, they'd be jumping up and down. Because storing data costs us a fortune. And we could do things like that. We could do that through clustering. We could do it through associative memory. We could have not only X's generating Y's, but we could have Y's generating X's. In other words, I could say, here's my X values, what's the Y that I get with it? Or here's what I'm observing, I get so many miles per gallon. What would the prototypical car be that could have that kind of miles per gallon? And it would be able to tell me what that looks like. One of the ones that I think holds the most promise and the most hope for us as industrial systems engineers are those neural nets that have adaptive capability. In other words, they can change themselves as they're being used. As they learn, they understand when something is novel enough that I've just learned something new, I need to change myself to accommodate that. Adaptive resonance theory, probabilistic neural nets, networks that have the ability to add or prune nodes or interconnections through some dynamic learning rule. All those things allow us to have adaptive capability. And with our computers, the memory being as cheap as it is now and as broad as it is now, it's very easy to set up adaptive methods where you can have millions, even billions of nodes in it, so that as new capabilities come up, the nodes increase or it could decrease, but increase in order to accommodate new clusters or new situations or whatever you're trying to train it about. That's phenomenal. That's amazing. You know, we have so many neurons in our head that we will never use in our life, but they're there just in case we need them. We could do the same thing in computation. Now, I'm giving you a lot of the cool things and why it's attractive. I'm going to tell you the other thing that's a downside of these. They don't explain themselves. It is next to impossible for me to open up a complicated neural net and derive a rule out of it per se. Yeah, I could get mathematical functions maybe out of it, but I can't get an if-then statement. It's very difficult. Okay, sometimes some slim networks you might be able to. Some networks are built so that the processing element isn't just a place that does an arbitrary computation, but actually has meaning. It represents something. I could point to that neuron, that PE, and say, that means this. It's a category. Or it represents a piece of data in my database. I could actually do those kind of things. And in fact, in those, I don't have to train them necessarily. If I know what they are, I could just encode them. I really think there's a lot to be said about the network paradigm for representing knowledge in general. Okay, not necessarily just a neural training that you would do, but that we actually can represent data, not necessarily in a table format, but in a network format. And you're seeing that a lot now with things like graph databases. There are neural nets where we do what's called interactive activation and competition, where if a processing element is fired, I could look at the other ones that are firing at the same time, knowing that what it basically is doing is interacting with those and actually activating them too. When that happens, I know there's a relationship with them. Conversely, I might see a processing element fire strongly and other ones fire in a negative sense. In other words, they're inhibited by it. Believe it or not, that's the kind of training that we could do. We could actually, and we use a lot in clustering, where here's the cluster the thing falls into. It's its nearest neighbor, if you will. But who else was it near to? Could it have been in if that one wasn't there? Could I actually rank all the ones I know about and say how well do they fit those? I'll come back and do another one sometime soon about what we call expert networks, where I'll actually show how I did that, where I had a neural net represent fuzzy logic. And it really did an incredibly good job. And again, one of the amazing things about this is it does not take $1 million software packages to do this. Not only to build them, there's stuff you can do on the PC, get for the PC, freebies out there. R is free, and it's got a neural net package in it. Okay, it doesn't have all the things I've just described, but it's got a lot of them. But deploying it is also a simple matter typically. It usually means somebody going back and writing a C program. In some cases, the thing can generate a C routine for you, and then all you have to do is bind it up and compile it into your system. You could have it as a separate black box or even a gray box if you want to. You could have it out in the cloud and link to it. You could deploy it in a spreadsheet. Believe it or not, most of the neural nets I've ever developed that are being used for analysis purposes have been deployed in spreadsheets. But the ones I think, again, that hold a lot of promise for industrial systems engineers, once you've got this mathematical simulation working, and you're happy that you've actually got your mapping or your clustering working well, you could deploy them in circuits. You could deploy them in chips. We have done that. You have them right now with you right now. If you've got a cell phone, you've got neural nets on there. They're in there as an integrated circuit or they're in there on the microchip. Yeah, things for adaptive capability, we got a little bit of way to go. You'd have to have chips that have extra space on it or circuits that have extra resistors and capacitors on them in order to do it that are basically doing nothing most of the time until they're needed. But that's okay. That stuff is getting very cheap, and for critical machinery, that might be okay to do things like that. Anyway, thank you for coming back and listening to this again, and I hope you got something out of it. I hope it whetted your appetite, if anything, about the possibilities of this. I always look at neural nets as being part of my bag of tricks. You know, I have all these things that I know of that can be used to solve problems and maybe even automate the solving of the problem. Discrete event simulation, all the stuff we have in OR and decision sciences, the data sciences stuff, our methods for managing and representing data, all that stuff is part of a bag of tricks that I think most industrial systems engineers who are going to be needed in the future will need to know about. If you want to call this part of the data sciences, feel free. I do, you know. But really, in the end, I think we are the data scientists of the future, and these are the type of techniques that we're going to be needing to use in the future, simply because we have so much data and we have very little time to put organization to it and put meaning to it, that we need to have things that are going to help us discover that meaning and help us do the organization of it. And these techniques can do that. Again, I will come back and do more types of neural nets and some other AI stuff. I talked about the new wave of AI. There's a lot more to it than neural nets. There's a lot more to it than machine learning. Knowledge-based systems, I think, are going to come roaring back, and I think it's worthwhile for us to have a seminar on that at some time. So look forward to that. I will make them very example oriented, like I did this, and I will actually talk about where I won't actually show you the thing, but I'll talk to you about applications that of those different techniques and how they're being used in the world right now. Some amazing stories, truthfully, and I love talking about them. So anyway, thank you very much, and if you need any information or guidance or pointing to references or anything like that, feel free to contact me. Thanks a lot.